GPU Architecture Basics. Intermediate Level. Parallel Processing Design. Introduction. GPUs are powerful processors designed to handle massive parallel workloads, especially for graphics and AI. Unlike CPUs, which focus on sequential execution, GPUs are built with many smaller cores, high memory bandwidth, parallel execution units. At the intermediate level, understanding GPU architecture means learning how GPUs are structured internally, how they process thousands of tasks simultaneously, how memory and cores interact, how GPUs differ from CPUs at the architectural level. What is GPU architecture? GPU architecture refers to the internal design of the GPU, including how its cores, memory, and processing units are organized. In simple terms, GPU architecture equals how a GPU is built to process data in parallel. Example concept. Many small cores means parallel execution, means faster processing. CPU versus GPU. Architecture feature. CPU, GPU. Core type. Few powerful cores, many smaller cores. Processing style. Sequential, parallel. Cache, large, smaller per core. Best use. Logic and control. Graphics and parallel tasks. Example concept. CPU means few strong workers. GPU means many workers working together. Core idea. Parallel processing. The GPU's main strength is parallelism. Task means split into many smaller tasks, means processed in parallel task, means split into many smaller tasks, means processed in parallel. Example. Rendering millions of pixels simultaneously, processing large datasets GPU core structure. A GPU contains thousands of cores. Streaming multiprocessors, SMs. GPU cores are grouped into units called streaming multiprocessors, SMs. Each SM contains multiple CUDA cores, shaders, registers, shared memory, control units. Example concept. GPU means multiple SMs, means many cores inside each SM, threads and warps. GPUs execute tasks using threads. Thread. Smallest unit of execution. Warp, group of threads. A group of threads executed together. Example concept. Threads means grouped means executed in parallel SIMD execution. GPU uses a model called SIMD, single instruction multiple data. SIMT, single instruction multiple threads. One instruction means applied to multiple data elements. One instruction means applied to multiple data elements. Example. Same operation applied to many pixels, GPU memory architecture. GPU memory is designed for high-speed access. Types of memory registers. Fastest memory per thread storage. Shared memory, shared within a block of threads, very fast. Global memory, VRAM, large but slower, accessible by all threads. Texture, constant memory, optimized for specific tasks. Example concept. Registers means shared, means global, means different speeds, memory hierarchy. Registers means shared memory, means global memory, VRAM. Registers means shared memory, means global memory, VRAM. GPU processing flow. CPU means GPU, means parallel execution, means result. CPU means GPU, means parallel execution, means result. Step by step. CPU sends task to GPU. Task divided into threads. Threads assigned to SMs. Parallel execution occurs. Results combined and returned. Graphics pipeline. Overview. Rendering graphics involves multiple stages. Pipeline stages vertices means rasterization, means fragments, means pixels, means display GPU in AI and computing. GPUs are widely used in deep learning data processing simulations. Example concept. Parallel processing means faster AI training performance factors. GPU performance depends on number of cores, clock speed, memory bandwidth, architecture design. Example concept. More cores plus better memory means higher performance bottlenecks. Performance may be limited by insufficient memory bandwidth, CPU bottleneck, inefficient parallel usage. Example concept. Poor parallelization means reduced GPU efficiency. Advantages of GPU architecture. Advantages include massive parallelism, high throughput, efficient for large datasets, ideal for graphics and AI. Example concept. Parallel design means high performance limitations. Challenges include not suitable for sequential tasks, complex programming model, high power consumption. Example concept. GPU means strong in parallel, weak in sequential tasks, concepts learned. GPU architecture basics, parallel processing model, streaming multiprocessors, memory hierarchy in GPU, threads and warps, GPU versus CPU design. Simple definition. GPU architecture. The internal design of a GPU that uses many small cores and parallel processing to handle large-scale computations efficiently. Final summary. GPU architecture is built around parallel processing, enabling thousands of tasks to be executed simultaneously. It uses structures like streaming multiprocessors, threads, and specialized memory systems to achieve high performance. Unlike CPUs, GPUs are optimized for handling large datasets and repetitive computations. Understanding GPU architecture is essential for learning computer graphics, AI, and high-performance computing.